This should be fine.
Oh, you are?
Yes.
On Saturday?
Okay, are you ready, spaghetti?
And they're going to watch.
All right, check this out. It's like it's a little tight.
I think so. I mean, this cars have been
All
spray.
right, if you figure out the secret, don't spoil it. John's already got it. Okay, I'm gonna put 3. These are all the same weight, all the same mass. Colin, just talked about this 5 seconds ago. Okay, if I put 3 of these
Okay, sorry.
on, let's say, the 8, so 3 on the 8. All right, who could guess or think about a combination other than putting 3 on the 8 that would balance it? 4 on 6? Let's see, 4 on 6. Oh, thinky winkies. So 4 on 6 balances out 3 on 8. That's good. Okay, good.
I was gonna say 6 on 4.
Okay, I'm gonna put. All right, let's try another one. Let's go. We'll put 4 on 9. So we got 4 on the 9.
4 on the 5 and 2 on the 8.
So 4 on the 5 and 2 on the 8.
Yeah.
Let's see if that works. Whoa. Pretty impressive. And just in case anyone's like, oh, is it just always balanced? No, if I take 1 off, it's very unbalanced. Okay. Okay, let's do another one. Like I said, don't give it away. Some of you guys probably already seen this before, so let's go 3 on the 10. So 3 on the 10. And you can be a combination on the side. Who feels brave wants to make a guess? 3 on the 10.
Get wrecked.
Wow, destroyed. Anyone? So I'll put a couple random ones on. I'll put 1 on the 8, 1 on the 7, 1 on the 4.
One on the 1, 2 on the 5,
1 on the 1,
1 on the 5.
and 1 on the 10.
Oh, that works too.
Cool. Cool. There we go. It worked. Okay. All right. What?
This thing. I
What-
played it for hours.
You have one of these?
Oh, if I did, I would. Okay.
So let's do one more. Last one. Okay. I'm gonna go. Let's go. 2 on the 5. So it's 2 on the 5. And then we'll go. Man down. Then we'll go 2 on the 3. Let's do one more, and 1 on the 10. Okay, so that's a lot. So 2 on there, 2 on there, and 1 on there. So if you figured it out, you can do the calculation now, right?
Yeah.
So I'll reveal the secret, right? 2 times 3, 6. 2 times 5 is 10, and 1 times 10 is 10. So if you add that all up, 10 plus 10 plus 6 is 26. So how can we make a 26 on this side? Well, how about, huh? 2 on the 10 and 1 on the 6? There we go. It's balanced. Okay, so what this is demonstrating is this, well, it actually demonstrates a couple things. It demonstrates an idea of torque, which we're going to cover later, because each one of these exerts a torque on the system. Torque is a Mr. Twisty. It's a rotational analog to force. But what we're really looking at for now is the center of mass. So when it's balanced, where's the center of mass of this bar? In the middle. That's how balancing works. So if you want to balance something, you got to put it on the center of mass. So I got a different demonstration for you. Okay. So let's suppose, this isn't going to be a perfect demo or anything, but let's suppose I want to balance this stick on, it's a meter stick, on this balancing point. Not very surprising that the center of mass is in the middle, right? But what if I wanted to put, say, this is a 500 gram weight, and this is a 200 gram weight. What if I wanted to put them, right? If I do that, then it's not balanced, right?
But if you slide the 5.
So yeah, obviously the center of mass is going to be biased towards this. So the balancing point is going to be somewhere here. So what I want to try is real quick to just calculate that. Could you predict where the center of mass is?
You said, Mr. Hall, did you say it was 200 on the other side?
It's a 200 and a 500.
So wouldn't you slide that one up just a little bit for the 500, just over half, like to like a,
You can probably reason out the answer. What I'm going to show you here is how to calculate it, because this is we're studying like formal methods of stuff here. So here's the meter stick. I'm going to represent the meter stick with a line segment. Okay. Hold on. I'll just do it low. Okay. So I'm going to call this position 0, and I'll call this position 100 for 100 centimeters, right? So it's a meter stick. And so if I'm going to put on the left side a 200 gram weight, and on the right side a 500 gram weight, where theoretically speaking is the center of mass. So what you do is you multiply, so you construct this coordinate system and then you multiply the weights or the masses times the distance, their position, just like on that. So you'd go 2, this marker sucks. That's the stinky one. There we go, I have some over here. Okay, so you'd go 200 times 0 plus 500 times 100. Now, if you do that, I mean, what do you get? You get 500, you get 50,000. You're like, wait, what is the meaning of that number? So the idea is then you would take this value and you would divide it. I'll be impressed if someone can guess the answer to what am I going to divide by?
700?
700. Very good. The total mass of the system. Not obvious, right? But you multiply each mass by its position, and then you divide by the total mass of the system. So let's see what. Anyone got a calculator? Can tell me what 50,000 divided by 700 is?
71.4.
it's going to be 20 something.
71.4. Okay. Now what does that represent? So think of the units here. This was grams multiplied by centimeters, right? And then what do we divide by? Grams. So my final answer is a centimeter value. And so the center of mass ought to be at 71.4 centimeters. Does that make sense?
Yeah.
Okay, so I'm going to take on my stick here, I actually have it backwards, sorry, let me just change it. So now here's where the 0 is. 0 is on the left side. And so I put it at 71.4 roughly. It should be pretty close. Now there's other little minor considerations that might throw off our calculation a bit, but tell you what it actually, okay, you can see it's balanced now, right? It's not, I maybe can push it a little bit over to the side. Now what's interesting is, if you look here, it actually is right around like 67 and a half. So this is where stuff like this can get interesting, is like why, what are some reasons why our calculation might be slightly off?
Could it be even the flex of the wood itself? Like absorbing?
Sure. One, this model doesn't take into account the flexing of the bar, right? The flexing of the bar would maybe throw off these numbers. There's another thing.
Oh,
What, Bailey?
The weights aren't actually all the way on the ends.
Very good. Exactly. So the weights are actually, I mean, like this one, in order for me to get it on a stick, it's actually the if you now you can go, what's the center of mass of this mass in relation to the stick? Well, it's like it's more at like 99 or something. So anyway, all I'm showing you is this is a theoretical calculation where we treated these as what they call point masses. We treated them like they're little tiny points that contain all the mass and set at these exact positions, and it's a perfectly rigid rod. And then you can see that, yeah, we got pretty close. Like calculation told us it was about here. What? Yeah, I got a haircut. Yes.
Talk about cover this.
I was,
Yeah. Okay. All right. Let's get into our material here. So that was. I hope that all made sense. If it didn't make sense, that's okay. I'm going to explain it as it pertains to our assignment. So, okay. So, is it Wednesday?
Yeah.
Short Wednesday. What time's class over?
Hey, don't you have like teacher meeting
49.
on Wednesday and stuff, Mr. Hall?
I don't think so.
I thought that was like you were.
I hope not. Soul crushed. I don't think so.
8:49, is that the right one? Wednesday?
Yeah, it's okay. We got 10, 15 minutes.
Okay.
So 14 is just asking us to calculate a center of mass. Okay. Now, by the way, just to kind of front load this, you might be wondering, well, we were just talking about momentum yesterday. Why are we all of a sudden talking about center of mass? Well, it's a big consideration. What we're going to be doing in the very near future is looking at, like, you take a whole system of stuff, and you can talk about the whole momentum of the system in relation to that system's center of mass. Okay. And so just in general, by the way, let me just throw this out here. If you want to really just actually on people, you can, like, here's one. What does the Earth orbit around? Actually, Trenton, the Earth and Sun orbit around the center of mass of the solar system.
Mr. Hall.
That's how you really make friends at the party. Is you actually people.
If you
Yes.
really want to actually someone, just say it's from the thrusters underneath the Earth.
Oh, there you go. There you go. No, it's actually an interesting fact.
Donut.
Yeah, and in any orbital system, the things are, I mean, the center of mass of the solar system, if you calculate it, is inside the sun. But technically, it's like, you ever heard of a binary star system? That's what happens there. If you have a star and a star, the center of mass might, I mean, if this star maybe is slightly heavier than this one, the center of mass might be like here, but they'll orbit around their center of mass. And the same thing's true of, like, you have a big old sun and a little tiny Earth. Well, the center of mass, if you calculate it, it's probably like here. It's an exaggeration. It's probably like a couple of feet away from the actual center of the sun. But technically, the sun orbits around that center of mass, and so does the Earth. What's up?
I feel like we could totally spice up the solar system just by orbiting. The Earth just slams into the sun.
That'd be good.
Wait, so that is the center of mass in the exact center of the sun?
It's on the exact center. So, like, we're going to see some calculations here that should hopefully shed some light on this. But, like, if you have the sun is so much more massive than the Earth that if you do the calculation and find, because the center of mass is just a point in space,
Right.
but if you find that point, it's in the interior of the sun.
Just a little bit off.
Yeah. So, like, it's not like profoundly wrong to say that the sun stays still. I mean, everything's orbiting around the galaxy, but, like,
Right.
say in the reference frame of the galaxy, of the solar system, the sun, for all intents and purposes, stays still, and all the planets orbit around it. But
Right.
if you look closely, the sun is orbiting around that's the center of mass of the whole solar system. Yes. bigly fast. It's really fast. I don't know the answer. Yeah, you have the Milky Way, right? And our solar system's like out here. So our solar system is rotating around the sun effectively, but then the whole solar system is orbiting around the center of the galaxy.
Yeah, like.
Which is, I think, as far as I know. The galaxy's not really orbiting anything, I don't think.
Saturn?
Just sort of.
I mean, maybe if you said theoretically all the galaxies have a center of mass in the universe, but my understanding is that they've observed that all the galaxies are they say the universe is expanding. Cosmologists say that the universe is expanding, so they'll find that the farther away two galaxies are, the faster they're moving away from each other. So there doesn't seem to be any like model where like all the galaxies are like in this nice
Yeah.
orbit around anything. If that makes sense. Feel free to, I'm not a cosmologist, fact check me on that.
Well.
Anyway,
Just chilling.
there's chilling.
Zooming everywhere. And they find a body and they're like, hey, let's merge.
Let's make a super galactic cluster or something.
Yeah.
What's up?
130 miles per second.
That's savage.
Yeah.
Okay, sorry. So on a one-dimensional track, here's the track. The track could be infinite. I mean, theoretically. Here's a track. And there's positions. So at position 10 so here's the origin. You can always define some origin on any number line. There's a 50 kilogram mass. 50 kilograms at position 10 meters. And there's a 30 kilogram mass at position negative 10 meters. So just using kind of basic reasoning, will the center of mass be closer to him or him? First guy, right? Guy on the right. So the calculation is very simple, okay? You go 50 times 10 plus 30 times negative 10. And you divide that by the total mass of the system, 80. So 500 minus 300 is 200. And again, what are the units of this? It's meters. Meters. So the center of mass is right here at 2.5. Center of mass. Okay, pretty easy, right? Well, it's gonna get more difficult, but for now.
Because like if you had like these multiple masses on each side, you just add them both up on. Like, so like if you just say you had a whole and all.
You could have 100 masses on this. I mean, you could, first of all, you could have 100 different masses in a three-dimensional space and still calculate the center of mass. It's just that now, instead of single numbers that describe their positions, it's going to be three-dimensional vectors, which makes things more complicated. But you can do it. That's just that's not like super complicated. That's just undergraduate level stuff. You could, if any of you guys study like engineering, for example, you'll probably take a class that involves like, you know, calculating theoretical mass centers of different distributions of objects. Solid.
So we have to look forward to.
If you add like a time in there for your fourth dimension, how the hell would you calculate that?
I was just
Like.
Well, if the system's evolving over time, you just have a time-dependent center of mass function. So like, we're actually gonna do that in this class. We're gonna show how if two objects are moving, right? We can calculate, so if we know how this guy's position depends on time, and we know how this guy's position depends on time, so we have two position functions, right? Then we can then make, with the same calculation, you can make a center of mass position function. And then what you can do is then you can say, what happens if you observe that system from the frame of reference of the center of mass? That's a bigly thing in physics. It's like taking a system and saying, what happens if we look at this system from the frame of reference of it? What if you were traveling along with the center of mass? What would things look like? That make sense? Sort of, kind of?
Yeah, and I mean,
Okay, let's do, we only got time for a couple more here, so let's look at 15. You got a 40 kilogram block and a 10 kilogram block are attached to a 6 meter long massless rod. The reason the rod is massless is, that's another thing I actually forgot to mention that with the stick thing earlier. That's one thing that also might have thrown off our answer is the stick has mass, right? This stick weighs, I don't know, might be like 50 grams, 100 grams, which contributes to the overall center of mass. So anyway, we're going to actually do that on 16. We're going to say what happens if the stick itself has some mass. So I think we'll have time to get to that. Let's look at, so 15 is actually pretty simple. You've got these two masses. This guy is 40 kilograms. This guy is 10 kilograms. And the stick is 6 meters long. So you have to be kind of clever and pick your coordinate system. All right, Zach, can you put that away, please? Where should we put the center? Where should we put the origin? You could put it in the middle.
You want to put it, the origin 0, so you want to put it at the first one.
You can put it here.
Yeah.
Why? It actually doesn't matter. You can do it however you want. So let's say you chose this as your origin. That's probably what I would do. I would choose the leftmost point as my origin, making this position 6, right? So it's my calculation. 40 times 0 plus 10 times 6, and you divide that by 50. And what do we get? 60 divided by 50, 1.2. Now you always have to interpret that number in context with what you're doing. If we had chosen our, yes, Aiden.
I put the origin in the middle and I got a good number.
Yep. So let's say we make this the origin. So I'll do this in blue. That's what I mean by you have to interpret the number you get in context. So 1.2 is like here-ish. So if we chose this as our origin instead, we should expect a negative number. Did you get negative 1.8? Right? So if you make this the origin, your calculation goes 40 times negative 3 plus 10 times positive 3 divided by 50, which gets you negative 1.8, which tells me, you see how that's the same position?
So it's okay to get it. Okay, so.
It's all about interpreting your answer. So saying that you're 1.8 meters to the left of the center of the stick is equivalent to saying that you're 1.2 meters away from the left side of the stick, right?
Yeah.
Make sense?
Yeah.
Okay. We're out of time. 16 will, unless you're feeling really ambitious, there's not a whole lot to kind of do because I have to explain some more stuff tomorrow. So if you're behind, you could get caught up, I guess, for homework. What's up?